All right, this is part 2 of the example problems where we're finding volumes of solids using integration, specifically the integration technique that was the first technique that was developed for finding volumes, where you're integrating the cross-sectional area formula over an independent variable. So in other words, you're breaking up the volume into right cylinders, because the differential element is that the cross-sectional area at some point that you're at along the length of the solid times delta x. So it's these right cylinders. And I want to point that out because we're going to see in the next section that we're going to develop another method to calculate volumes of solids, that it works in certain situations. This other method works better. So by other method, I mean that we're going to break the solid up into pieces in a different way than the cross-sectional area method. All right, but for this video though, we're using the cross-sectional area method. So let's find the volume of this solid here. The base is a circular disc with radius r. The parallel cross-sections perpendicular to the base are squares. All right, so the idea here is that you've got this circular base, and we're going to walk along the base like this. This is perpendicular to these squares here. We're going to walk from one side of the circle to the other. Now, we don't have to. I mean, we could walk from here to here across. That's fine. But then how are you going to get the cross-sectional area formula in that case? I mean, if you can get that formula, then that's fine. You could do it. But, you know, we want to walk perpendicular to the squares so that at each point along the circle, the cross-section of the plane that cuts through that point that we're at is going to be a square. It's going to cut a cross-section, a square cross-section. So we're going to walk along the base of the circle from one end of the circle to the other. So, you know, you think, well, let's, you know, maybe put the starting point here, but, you know, the math should be a lot easier if we put the center of the start at the center of the circle, put the origin at the center of the circle as opposed to the origin here. But you could do that too. You could put the origin here and you'd still get the same answer as long as you do the integration right. But okay, so we're at here's the center of the circle, and we're going to be walking from one side of the circle to the other. And so that we're going to be walking from minus r to r. And we'll say this is y. You know, up and down, we'll say this is where in the y, the independent variable is y. Okay, and so this is x. Here's y. Okay, now what we want to do is we want to get a formula for this distance here. For any y that from minus r to r, for any y value that, again, going from minus r to r, we want to input that y and get this length here. And when we have that length, then it's easy to get the cross-sectional area. But let's first get this length here. So we're at this point y. This is y. Okay, and what else do we know here? This is r, the base, the disc base, and we want to find this length here, but we're going to use the Pythagorean theorem to get this length here. So let's call this a divided by 2, because then in that case this will have a side length. This is the side length of a square. The side length of a square is a. So we want to solve here for a divided by 2. And so with the Pythagorean theorem, we've got y squared plus a divided by 2 squared is equal to r squared. Okay, so let's solve for a. So 4, multiply the entire equation by 4, you've got 4y squared plus a squared is equal to 4r squared. Okay, a squared is equal to 4r squared minus 4y squared, a squared is equal to 4r squared minus y squared. Okay, so now we take the square root of both sides, but we don't have to put plus or minus because we're like, I'll show you why. So okay, we get a is equal to 2 root r squared minus y squared. So if we put plus or minus, then we'd have plus or minus 2 root r squared minus y squared. And what that would be referring to is, so we just, like, so for every y, what are we solving for? We're solving for like this point. That's really what we're solving for. This a divided by 2, we're just saying, okay, like we solve for a here, but in reality, what we're doing is we're inputting a y and finding this x. That's what we're doing. And so the plus or minus is just saying, it's saying, okay, a solution is this point and this point, right? This a divided by 2, you could just put x, right? You could just say that's x. And so what you have is y squared plus x squared is equal to r squared. And so if you solve for y, it's telling you that for any y, you've got 2 points here. You see? But that's not necessary. We could just use the math this way. So we can neglect the plus or minus. And now here, what we've got is we can input any y from even if it's minus y to y, and it's going to give us what we want. Minus y to y, from minus r to r, you input a y, it's going to give you this length as a magnitude. That's what we want, okay? All right, so now a of y, that's the, for any position y from minus r to r, what's the cross-sectional area? It's just this squared. 4r squared minus y squared. There we go. So now to get the volume, we're just integrating from minus r to r, that a of y, 4r squared minus y squared dy. That's it. So, okay, we could take out that 4. We're going from minus r to r. So you've got r squared y minus 1/3 y cubed. And then we'll integrate this from minus r to, we're taking this from minus r to r. So, okay, we plug in r, we get, for y, you get r cubed minus 1/3 r cubed. Okay, now minus, and then plug in minus r, and you get minus r cubed plus, because the minus r will stay minus here, 1/3 r cubed. So we've got 2/3 r cubed minus 1 plus 1/3 is minus 2/3 r cubed. So this is 2/3 r cubed plus 2/3 r cubed, which is 4/3 r cubed, so 16/3 r cubed. Okay. The solid S is bounded by circles that are perpendicular to the x-axis, intersect the x-axis, and have centers on the parabola. Y is equal to 1/2 1 minus x squared. X goes from minus 1 to 1. Okay. So we want to find the volume of this solid. And so what is it saying? The circles are perpendicular to the x-axis, have centers. They're centered on the x-axis. They intersect the x-axis, but their centers are on this parabola here. So let's see if we can draw this and get a sense for what's going on. So there's x, there's y. Let's say we're going from -1 to 1. This is x. So y is equal to 1/2 minus 1/2 x squared. All right, so when x is equal to 0, y is equal to 1/2. So, okay, let's say these have the same scale. So about, there's 1. So when x is equal to 0, y is equal to 1/2. When x is equal to 1, y is equal to 0. When x is equal to -1, y is also equal to 0. So this is going to be parabolic, something like that. Okay, so now the idea is, as we're going to walk from -1 to 1 because that's the best option here, because these circles are perpendicular to the x-axis. So if we're going to use these circles for our area formula and use the circles in the sense of just like pi times the radius squared, we want to be walking perpendicular to the circles. So that's the case. We're from -1 to 1 along this x-axis. We're going to be perpendicular to the circles. Okay. Now the idea is, so we're not going to be walking along this. If we walked along this, we wouldn't be perpendicular to the circles. We're going to be walking along this. But this comes into play how? Because this is where the centers, like, so if I'm here, I'm perpendicular to a circle. I am perpendicular to a circle when I'm here. The center of that circle is here. Okay? And so that's good information. But another piece of the information is that the circle intersects the x-axis here as well. And what does that mean, intersects? That doesn't mean that, like, so here's the circle and the x-axis goes through the circle. No. You know, nothing. When they say intersects, they're talking about the equation of the circle. So the x-axis intersects the circle. Okay, so how does that help us? How does that information help us to get, we want, we're going from x at this x is equal to -0.8, whatever this is. We want the area of that circle here that's centered here and that intersects the x-axis here. We want the area of that circle. Well, okay, if this is the center of the circle and the circle intersects here, well, then we know that this distance here is a radius of the circle. The center is here, and we're drawing it to a point on the circle. That's a radius. Think about a circle. If you start, you're starting at the center, and you draw a line from the center to any point on the circle, that's you've gone a radius. So what this tells us is that y is equal to r. So for any point x is equal to -1 to 1, you plug it into here, into this function, and you get r for that point. So in other words, r is equal to 1/2 times 1 minus x squared. So the area formula is what? Pi r squared. Pi times 1/4 1 minus x squared squared. Okay, there we go. Let's simplify this. This is x to the 4th. Okay, so now the volume is just, we integrate from -1 to 1 a of x dx. So we can bring out the pi over 4, and we got 1 minus 2x squared plus x to the 4th dx. So we've got x minus 2/3 x cubed plus 1/5 x to the 5th. Integrate from, we're going from -1 to 1. Okay, so you've got pi over 4. Okay, let's plug in 1. 1 minus 2/3 plus 1/5 minus, okay, minus 1 plus 2/3 minus 1/5. Okay. 1 minus 2/3 is 1/3. So you got 1/3 plus 1/5. Minus 1 plus 2/3 is minus 1/3. And so we can plug this into our calculator. Okay, and then all right, and then this minus this. 16/15. Pi over 4 times 16/15. So pi over 4 times 16/15. So it's 4 pi over 15.